Welcome to the lesson about base conversion. We are still in the part of base 2, and we will actually work with some other kind of bases and see how to convert from one representation to another representation. Objectives of this lesson. You will learn about 3 ways to convert between different number representations. You will understand how to choose the right way for every case of conversion. You will experience conversion of numbers between the binary and decimal systems and vice versa. Why is this important? You work with decimal numbers most of your life. Sometimes you would like to know what a binary number looks like in decimal. You might see some strange number made of ones and zeros and you want to know what is it. A second reason that this kind of knowledge is important is that you need to know how to decode decimal numbers into base 2. Why? So you could give a number to the processor. The processor can't understand your decimal numbers. Another reason is this. Understanding conversion methods will unexpectedly give you some new insights about numbering systems. This might be surprising, but it is probably true. The more ways you have to see numbers, the more ideas and insight you are probably going to have about numbers. This might be true about anything in life, but about numbers specifically. Something very basic. We actually, I think, seen this before. Conversion from binary to decimal. The problem is this. We are given a binary representation of some quantity, and we want to find its decimal representation. The conversion is really straightforward. We just calculate the value of the number according to the definition. For example, we have this number 1011 in base 2, and we want to get the decimal representation. Maybe we want to get a better feeling of this number. So we just calculate its value, and it goes like this. We begin with the rightmost 1 digit, this bit, and we calculate 1 times 2 to the 0 plus 1 times 2 to the first plus 0 times 2 to the second plus 1 times 2 to the third. Now, it is interesting to see that these digits 1, 1, 0 and 1 is actually the digits of the number 1, 1, 0 and 1. If we keep calculating, we get 1 plus 2 plus 0 plus 8, which is 11 in base 10. Another example, you could look at it for a few seconds just to make sure that you understand. The calculation is mostly the same. It's just a longer number this time. This side of the conversion is pretty easy. Mostly because we are used to calculation in base 10. So we could actually calculate this part or this part very easily. Why? Because we know how to multiply in the decimal base and we know how to exponent in the decimal base. So it is mostly easy. It works for other bases too. What I mean is, it doesn't have to be the binary base. It could be, for example, the trinary base. For example, look at this number, 12011 in base 3. We calculate it mostly the same. It's just that the exponent is 3 this time instead of 2. So we calculate it like this. 1 times 3 to the 0 plus 1 times 3 to the first plus 0 times 3 to the second and so on. Eventually, we can actually calculate the values and we get 1 plus 3 plus 0 plus 54 plus 81. And that is 139 in base 10. If you want to check these kind of things, maybe using a computer just to make sure that you see things straight, and I don't know, maybe just to check yourself out, as usual, you can use the calculator. If you're using Windows, and I hope you do mostly for this course, then you could pretty easily just take the Windows calculator and check it out. Thinking about it, I think every operation system that respects itself should have some kind of this calculator, so it's not really a problem. Let's check it out. Let's put some number inside, for example, 139 that we have here. We can see that we could choose another base, for example, the binary base, and we get an interesting number. Well, maybe it wasn't such a good choice because here this is the ternary base, so we could check, for example, the number 30 here. 30, we move it to binary, and we get this number, which is mostly like our result. So we were right. The first method that we talked about is the direct evaluation. That is what we've just seen. We'll try to define it maybe in a more strict way. The problem is something like this. We are given a decimal representation of a quantity, and we want to find the binary representation of this quantity. It could be something else. It could be maybe the trinary representation or base 5 representation, but mostly we are going to work with the binary representation. So that's what I'm going to talk about. For example, what is the binary representation of the number 13? The direct evaluation way would be something like this. We know that in base 10, the value is calculated in this fashion. 3 times 10 to the 0 plus 1 times 10 to the first. So, if we really want to use this method to calculate the base 2 representation, we couldn't. Actually, we'll have to convert everything to base 2. That means we will take this 3 and convert it to 11, and 10 is being converted to 1010. You can check it out yourself. This should be 10. And also we convert this 1, which just stays 1, and we convert this 10, which is 1010. We get this strange calculation, which is 11 times this number and 1 times this number, and this time we have luck because everything is pretty small. The result of this exponentiation should be 1, so we just get 11 here. And the result of this is just 1 times this strange number, 1010. So we get plus 1010. And because we know how to add binary numbers, we could get this result. There are some cons and pros to this method. Maybe the stuff that are not so good about it is that we had to know that 10 decimally equals this binary representation. We had to know it ahead of time. We also have to know how to multiply an exponent in base 2, which is not very easy for human beings. This is just like the case of converting binary to decimal. However, here the calculation is not very comfortable. In the other direction, it was pretty easy. We could just multiply and calculate and do this on paper by ourselves. But here it might be a bit different. Think, for example, what would happen if you had to exponent this number by 3, for example. It wouldn't be very nice. It's not so fun for someone who is used to base 10. Though it might be fun for a computer. Maybe we could try something else. We are still talking about converting some decimal number to binary. This time we will introduce a different method. We will call it finding the largest power. Again, we are looking at the same example of trying to convert 13 in base 10 to the binary base. And we will work this way. We know that the binary representation is just sums of powers of 2. So what we are going to do is this. We will try to find the largest power of 2 that fits into 13. Well, we could just try a few and find out pretty quickly that the last one is 2 to the third, which is 8. Okay, because the next one is just too large. So we could take this quantity out of 13 and we are left with 5. Now we keep doing it again. We look for the largest power of 2 that fits into 5. And this is 2 to the 2, which is 4. We then subtract this number from 5 and we are left with 5 minus 4, which is 1. And lastly, largest power of 2 that fits into 1 is just 2 to the 0, which is 1. And then we are left with nothing. And we are done. We marked by the red color those numbers. Those numbers are the powers of 2 that were fitting into the number. So we conclude that 13 in base 10 actually equals 2 to the third plus 2 to the second plus 2 to the 0. Which is something like this. Here we added this one, which is prefixed by the 0. And the number that we get is 1, 1, 0, 1. Some very interesting fact here is that every number could be composed to a sum of distinct powers of 2 in a unique way. This is kind of interesting, because what would happen if we chose something else? I leave it to you to think about it. Maybe there is another representation of this kind to 13. You will probably have even more time to think about it in some of the exercises. Now we speak about a third way, which is very common. It is called the remainder evaluation. At least that is how we call it in this course. Again, we are trying to solve exactly the same problem. We are given a decimal representation of some quantity, and we want to find the binary representation. Again, we will work with the same example of 13 in base 10. How is this going to work? We are going to try to find the first binary digit. If we formulate it in another way, we want some kind of number that looks like this. I will try to explain what does it mean. We can see here a few digits. This is the lowest digit. It is called B0, and another digit next to it called B1, B2, B3, and so on, because I don't know at this point how many digits will be required. And all of this is in base 2. This should be equal to 13 in base 10. If we expand this expression, we are going to get something like this. B0 times 2 to the 0 plus B1 times 2 to the first, and so on. This should equal 13 in base 10. An interesting question at this point is this. Could the number 13 reveal anything about the values B0, B1, B2? Maybe it could leak somehow information. Maybe I could guess by looking at 13 what would be some of the bits. We could conclude, for example, this. 13 is odd. You probably remember that there are odd and even numbers. Odd numbers are those that are not divisible by 2, and even numbers are those that are divisible. 13 is not divisible by 2. If we formulate it more mathematically, then 13 is equivalent to 1 modulo 2. Therefore, the sum on the left must be odd. What does it mean? This sum must be odd. Why? Because 13 is odd, and those two are equal. So all of this must be odd. If we look closely at the sum, we could see that most of the summands are already divisible by 2. For example, this summand actually equals 2 times B1, which must be divisible by 2. Also this one, B2 times 4, must be divisible by 2, and so on. All the other elements must be divisible by 2. Except for this one. The first one, it could be not divisible by 2. For example, if B0 is 1. Therefore, we conclude that B0 must be 1. We mark it here by the green color. After we concluded this, we want to move on to the next level. So we could remove B0 from both sides and then divide by 2. We remove it from this side and from this side. We are going to obtain this new equation, which will look something like this. First of all, the number is going to be the same except for this digit, B0, which will disappear, and we have this new number. The new equation we are going to get is something like this: B1 times 2 to the 0 plus B2 times 2 to the first, and so on. You can see that we actually divided here by 2, all the elements, because all the powers are lower by 1. And we get on the other side 13 minus 1 divided by 2, which is 6. We have a new equation. We kind of reduced the problem. First, we wanted to know how to represent 13 in base 2. Now we are trying to solve a smaller problem. We try to solve the problem of finding the representation of 6, which is about half of the original number, which is very encouraging. If we were going to do this a few times, we could expect that eventually we just get the final answer, because the numbers just get smaller and smaller every time. And even pretty fast, they get smaller and smaller by a factor of 2 every time. Let's try to find the second digit. Again, we ask the same question. Could the number 6 reveal anything about the values B1, B2, B3? And the answer is, of course, just like before. 6 is even, and mathematically speaking, we could say that 6 is equivalent to 0 modulo 2. Therefore, the sum on the left must be even. Which sum are we talking about? Just like this sum, we could create an equivalent sum here. We have to get that B1 is 0. We could then remove B0 from both sides and then divide by 2. Notice that since B0 equals 0 this time, we don't actually remove anything from both sides. We just divide by 2. But we could think about it as subtracting 0 from both sides. Then we divide by 2. And we get again a new equation that looks something like this. Now, note that the number now is again divided by 2. And we reduce the problem even more to just finding the representation of 3. And we just keep going. I don't want to do this here because it might be tiring for you to watch me doing this. But don't worry, you will have the opportunity to do this yourself. Let's look at how to do it in a systematic way, because this method is pretty important. You are probably going to use it in one way or another. So it's important to know how to do it and even how to do it fast. We will usually use some kind of table to invoke this method. In every step, we check the remainder of the number in the left when divided by 2. We then write the remainder on the right side of the line and the result of division by 2 in the left side of the line. Let's look at some kind of example. We have here the number 13, and we want to understand how to represent it in the binary base. So every time we just try to divide it by 2 and find out the remainder. I hope you do remember what a remainder is. It's that thing that you learn in elementary school, really in the beginning, and then you forget about it when you buy a calculator. Let's see really what happens when you try to divide 13. Let's move to the standard mode. That's how usual people use the calculator. And try to divide 13 by 2. Okay, we get 6.5. And what does that actually mean? That doesn't give the remainder. It's not what we want here. The remainder is something else. How could we get it? We take 13, we divide it by 2, and we get it is about 6. So, if it is 6, multiplying by 2, we get 12, which is almost 13. It is not 13. The remainder would be something like this. It would be 13 minus 12. It would be 1, which is this remainder. Whenever you divide a number, you get two results if we are talking about integers. You get the quotient and the remainder. The quotient is the actual result of the division, but the quotient is always an integer. And the remainder is what's missing to get the actual original number. So here, 13 divided by 2, we get 6. Okay, that's where we write the quotient. And the remainder is 1. What does it actually mean? It means that 2 times 6 plus 1 is going to be 13. Okay, I will repeat it. 2 times 6 plus 1 equals 13. We are going to move to the next step. Now we are working with 6. So we try to divide it by 2 and we get the remainder of 0 because 6 is divisible by 2 and the quotient is 3. Again we can see that 2 times 3 plus 0 equals 6. This is the invariant of this table. Whenever you look at this kind of table, you could be sure that this never changes. That you could always pick some number, for example 3, multiply it by 2, and add the number on this side and get 6. Okay, now we go on with 3. We try to divide it by 2, and we get a remainder of 1, because 3 is not divisible by 2. And the quotient is also 1, because 1 times 2 is 2, which is almost 3. Finally, we keep up with the last number, which is 1, and we try to divide it by 2, and of course we are going to get a remainder of 1. When we get 1, we just stop. We don't continue putting numbers here. And eventually, the result is going to be on the right side of the table. And we have to read it from below to the high part. The highest digit is going to be the one lowest in the table, and the lowest digit is going to be the one highest in the table. It might be confusing at first, but you are probably going to get used to it. This method is very interesting because you get the digits in the opposite order. In the beginning you get the lowest digit, and in the end you get the highest digit, because we are using the remainders, and the remainders give us the lowest digits first. And again, just like the other method, we get that 13 in base 10 equals 1101 in base 2. Just make sure for a second that you see that the numbers are equal. Nice, let's move on.